everybody, welcome to the first pre-recorded lecture. Let me just remind you what we did last time. So I just posted the homework, which is going to be due next Friday. So a reminder, first let me briefly mention the Catalan numbers. Last time we were talking about Catalan numbers, which are denoted Cn. Right? Cn is the number of Dyck paths inside, well, from 0, 0 to n comma n. So what is a Dyck path? A Dyck path is basically a northeast lattice path in which stays above the diagonal, above the main diagonal, the line y equals to x. So, and I mentioned and I proved the formula that Cn is 1 over n plus 1 times 2n choose n. I proved this formula by a reflection principle, which makes it completely still not obvious why would this number 2n choose n be divisible by n plus 1. But since we know it's the answer is integer, then it's divisible. But yeah. So as I mentioned, I'm a big fan of Catalan numbers. So I'd like to start this lecture. Again, this is not going to be in the homeworks or the midterms, but let me just briefly mention a few families of combinatorial objects which are also counted by Catalan numbers, because there is. You'd be surprised by how many just completely unrelated looking combinatorial objects there are. There is a book by Richard Stanley which contains like 200 plus different combinatorial interpretations. Yeah, so let me mention the first few of them, which I think are the most natural, I guess. So combinatorial interpretations of Cn. And okay, so the first one, as I already mentioned, Dyck paths. And for each of them, what I'm going to do is I'm going to draw the 5 objects. So there should be, right, the sequence goes C1 is equal to 1, C2 is equal to, well, 2, C3 is 5, C4 is 14, and then it goes like 42, and etc. So what I'm going to do is I'm going to draw the corresponding 5 objects for each interpretation. And yeah, for Dyck paths, I already did this last time. You take an n by n square, you draw the diagonal, and then so I'll just try to do this 5 times. Because at the end, what's going to happen is that you're going to look at all these collections of objects, and you're going to see that they look completely unrelated to each other. And the first one is Dyck paths. 1, 2, 3, 4, 5. Okay. Well, the next interpretation, which I think is kind of, well, it was also mentioned last time, is the standard Young tableau of shape which fit inside a 2 by n rectangle. So again, I drew these last time, but just to remind you, 1, 2, 3, 4, 5. Yeah, so I'm just going to put increasing numbers into these. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so and I explained a bijection between these two last time. even though proving that it's a bijection was an exercise. So, all right, now let me try to reveal a few more, which it's kind of tricky. It's much harder to come up with bijections for what I'm about to explain, but the objects themselves are very natural. So the third one is triangulations of an n plus 2 gone, which yeah, it's exactly what you think it is. So you draw a let's say a regular or arbitrary polygon. So if n equals to 3, then I have to draw a pentagon, and then you just want to subdivide it into rectangles. Yeah, let me even okay, here's 5 pentagons. So how do I subdivide a pentagon into triangles? Well, here is one way. So the vertices of the triangles have to be a subset of the vertices of each pentagon. So basically, I can kind of just, there's only one triangulation which I can rotate, and I get all possible triangulations of a pentagon. So maybe if I draw a bigger, let's say I draw an octagon. Okay, yeah, then I can try to draw a more complicated triangulation, maybe something like this. So the goal is to end up with a bunch of triangles whose union is the whole polygon. And so the claim is that the number of ways to triangulate this n plus 2 gone is also given by the Catalan number. And you can see that these objects are pretty different than these objects, right? Like for triangulations, there is a circular symmetry. If you rotate a triangulation n plus 2 times, you get back to your original triangulation. Okay, now, but it keeps going. There's so triangulations, and the next one is non-crossing matchings of 2n. Non-crossing matchings of bracket 2n. Oops. So what do I mean by a non-crossing matching? Let's say you draw a circle, and then you put 2n elements. So if n is equal to 3, then I put 1, 2, 3, 4, 5, 6. That's going to be my 6 numbers. So yeah, well, let me copy this a few times. So okay, now question is, I want to find matchings. So I want a perfect matching. So I have to match every element to a unique other element. And how many ways can I do this? Well, let's try. Maybe I can match everybody to its neighbors. I can do this in 2 different ways. Or I can match like this. And I can also do this yeah, I guess that's all the possible ways I have. So yeah, I got 5 numbers. I mean 5 matchings. And in general, it's going to be Catalan. If you increase the number of points on the boundary, it has to be even. So again, it's very tricky to find a bijection, because for here you can also rotate, but the rotation is going to be of order 2n. You have to rotate 2n times to get back to your original matching. So so the bijection, when you find the bijection, it somehow has to break the cyclic symmetry to go from here to here. Okay, the next one is going to be also another non-crossing object, which is non-crossing partitions of bracket n. So again, what I'm going to do is I'm going to, let me first try to draw a bigger example. So let's say maybe I take 10 and maybe n equals to 10. So I put numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the circle, and then I'm supposed to find a non-crossing partition. So which means that I have this set of 10 elements and I partition it into subsets, so that in a non-crossing way. So there cannot be a subset that looks like this and another one that looks like this. Right? These two are crossing, so that's not allowed. Okay, so I can try. Maybe I take 8 and 3, and then 2 is by itself, and then maybe 1 and 9 are together. 10 is by itself, and then 4, 5, 6 are together, and 7 is by itself. So question is, if I take bracket n, so I only take when n is equal to 3, I only take 3 elements. 1, 2, 3. So, and then I'm going to try to, maybe I should draw a little circle. No, that's not, anyways. Let me try to do this 5 times. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So the first partition is I can make every element into its own set. Or I can put these two together. I can have 2 elements together. Or I can have all 3 elements together. So that's non-crossing partition, and there is 5 of them. And maybe, this is actually a good example for me to compute the, remember there is C3 is equal to 5 and the next one is 14. So maybe I can try to count the 14 objects. C4 is equal to 14, which, is you can 1 over 4 plus 1 times 8 choose 4. Is that, that's supposed to be 5, 6, 7, 8 over 5 times 1, 2, 3, 4. You cancel 2 and 4 with the 8, 5 with the 5, and 6 with the 3. So you get 14. So okay, and now if I want to count non-crossing partitions, then I have to have 4 elements, and then I count in how many ways can I. And of course, I'm not going to write down all the 14 possible ways, but maybe what I'm gonna do is I'm gonna use the cyclic symmetry. So maybe again, if I take all singletons, then there is going to be 1 partition like this. If I take 2 adjacent elements together, then I can rotate this, right? I can take 1, 2, or I could take 2, 3, or 3, 4, or 1, 4. So there is like 4 possible options. And there is another way where I can take 1 and 3 together, or if I rotate, then I'm going to get 2 and 4 together. So there's kind of 2 rotations of this non-crossing partition. And finally, I can also take 3 elements together. So there is 4 rotations of this. And finally, I can take the whole set together, and there is 1 rotation of this. So if you sum these up together, oh no, am I missing something? Oh, okay, there is, there is 1 more. So 1 more, which is that I can take 2 plus 2, and there's 2 rotations of this. And if I sum them up together, then I get, hopefully, yes. So the total is 14. which again, so and you can see that in all these three examples, the cyclic symmetry acts differently. Here it has order n plus 2 for triangulations. For matchings, it has order 2n. For non-crossing partitions, it has order n. So yeah, it's pretty kind of deep if you think about it, because all these objects are very natural, but finding bijections between them is pretty tricky. So yeah, it's a nice exercise. Okay, there's more. So another object is parenthesis sequences. Parenthesis sequences, which so what I'm gonna do is you have n opening parentheses, or I'm just gonna say brackets, and opening brackets like this, and n closing brackets like this, and you're trying to shuffle them together so that they form a valid parenthesis sequence. So like valid means that every opening parenthesis has to match some closing parenthesis. So this would not be okay. This, yeah, maybe a sequence like this is not okay, but a sequence like this is okay, because every open parenthesis matches the closing one. So yeah, I mean the valid ones are those that you can see in an algebraic formula. So what are the 5 objects? Well, I have n. I have to have 3. N is equal to 3, so I have 3 opening ones and 3 closing ones. So yeah, I can do 3 opening and then 3 closing, or I can do something like this, or something like this, or also maybe something like this, or yeah, there's 5 objects. Again, yeah, it's pretty easy to see that such parenthesis sequences are in bijection with the dig paths. If you just kind of make every opening parenthesis into a north step, and every closing parenthesis into a south, into an east step, then you like 3 north and 3 east would give you a dig path which goes up and then to the right. So you can see each of them. You can map them pretty easily to dig paths. But yeah, it's still hard to do this for the other objects I mentioned. And finally, yeah, there is also going to be, so later I'm going to discuss Catalan numbers more in later lectures. So there's going to be plain trees, and there's going to be binary trees, and etc. So maybe should I try? Yeah, we're gonna talk about these later. So I'm gonna explain. I mean, you try to draw the number of plain, let's say, complete binary trees. Maybe you draw something like this. So what is a binary tree? A plain binary tree means that every vertex has a left child and a right child, except for the leaves. The leaves have no children. So yeah, and that's it. You just count how many binary trees you can make with, let's say, 4 leaves. Binary trees with n plus 1 leaves. And then you see that the answer is going to be Catalan number as well. Okay, so yeah, but I'm going to discuss this later. Now, for now, we're basically done with the Catalan numbers, and I want to go back to binomial coefficients. because there was a few properties which I did not mention. I started talking about lattice paths, and then I decided to kind of go into the Catalan direction. But yeah, there is more to say about binomial coefficients, which is going to be more useful to us. So, and the main property which was mentioned by you a few times in the previous lectures is the famous property of the Pascal triangle, which is that whenever you see a number, each number is equal to the sum of the two numbers above it. So 35 is equal to 20 plus 15. 15 is equal to 10 plus 5, and etc. So in proposition form, that becomes n. So that's only works for k strictly less than n, and choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. Okay, and so how do I prove it? And as usual, there is going to be two different proofs. One proof is going to be well, actually both proofs are going to be combinatorial. So proof number one. Proof number one is you just use the subset interpretation of binomial coefficients. So the right hand side is just n plus 1 choose k plus 1, so it counts k plus 1 element subsets of bracket n plus 1. Now, hopefully the left-hand side counts the same objects but in a different way. And indeed, so you consider two cases. You just look at each such k plus 1 element set, each such subset of n plus 1 set either contains n plus 1 or it doesn't contain n plus 1. So if it contains n plus 1, then so you're supposed to choose a k plus 1 element set, and you know that it contains n plus 1, so there is n choose k options. For the rest, right? Because yeah, you have to choose the remaining k elements out of the remaining n elements. If it doesn't contain n plus 1, then all of your k plus 1 k plus 1 elements have to belong to bracket n. So then you get n choose k plus 1 options. And yeah, now, so this is a typical example of where you would use the addition principle. So, right, you consider two cases where either it contains n plus 1 or it doesn't. So the game is always to just to split into cases in a clever way, just as I did right now. So yeah, that's the end of the proof, end of the first proof. So, and the second proof is going to be also combinatorial, but it's going to be using the geometric interpretation in terms of the lattice paths. And as one of you suggested at the last lecture, you can prove the lattice path interpretation using this identity. So yeah, the idea is that each of these three terms counts some lattice paths. So let's see. Let me try to copy the formula. Okay, so I start, let's say all paths have to start at 0, 0. Then, as you remember, if I have some point a comma b, then the number of lattice paths are going to be given by a plus b choose b. So in other words, I have to subtract, like the horizontal coordinate is just the bottom number, but the vertical coordinate has to be the difference between the top number and the bottom number. So, okay, n choose k counts lattice paths from 0, 0 to n minus k, comma k. Now n choose k plus 1. The vertical coordinate has to be bigger, so and it counts. Yeah, let me n minus k, comma k, and then n choose k plus 1. It's going to be on top and to the left, because the horizontal coordinate is n minus k minus 1, and the vertical coordinate is k plus 1. And finally, let me choose some other color, green, n plus 1, choose k plus 1. The horizontal coordinate is n, and n minus k, and the vertical, yeah, so it's the point over here. It's n minus k, comma k plus 1. So the claim is that if you start at 0, 0, then the number of lattice paths that terminate at the green point is equal to the number of lattice paths that terminate at red plus the lattice paths that terminate at blue. And yeah, indeed, that is true, because every path that starts at 0, 0 and terminates at the green point has to pass through either the red or the blue, but not both of them. It cannot pass through both red and blue. So yeah, each path terminating at the green point n minus k, comma k plus 1 has to pass through either the red point n minus k, comma k, or the blue point n minus k minus 1, comma k plus 1. And therefore, by the addition principle, you get to sum. You have to take the sum of these two numbers. So, and okay, in your homework there is a problem where you have to do pretty elaborate combinations of addition principles and product principles. So let me just kind of as a preview, or just let me try to do one practice problem which is sort of similar to the homework one, and yeah, it's similar to the ones above. So in general, there's many binomial coefficient identities you can prove. So let me give you one of them and explain how to prove this. So the proposition is that 2n choose n is equal to the sum for k from 0 to n of n choose k squared. Let me see if I can do an example of this. Let's see, maybe n is equal to 3. Would that be all right? So here's 6 choose k, right? That's this row is 6 choose k. So the claim is that 2n choose n, which is 20, should be equal. Yeah, that's okay. Let's say this is 2n choose k, but then I also have n, which is 3. This is n choose k. Right. So and the claim is that the sum of the squares of these numbers, which is 1 plus 9 plus 9 plus 1, is supposed to be equal to 20. which it sounds kind of similar to what we did in the first lecture, where we summed the numbers of standard Young tableau. But I mean, this is much easier to prove. So why is 20 equal to 1 plus 9 plus 9 plus 1? Well, the idea is to just look at this formula. One powerful way is to interpret both sides of the formula as counting the same types of combinatorial objects, but in a different way. And it's very easy to do for the left-hand side, right? It counts lattice paths. Okay, so proof. I'm trying to prove this formula. Let me copy. So the left-hand side, to n, choose n, counts. It counts lattice paths. Counts lattice paths from 0, 0 to n comma n. 0, 0, and maybe somewhere here is n comma n. And then you just count all lattice paths. So hopefully the right-hand side also counts these lattice paths in a different way. And you can see there's n choose k squared. So it seems to count some sort of pairs. There's a sum over k over some sets of pairs. So now, by the way, now is a good point for you to pause the video and try to figure it out. What is the way the right-hand side counts these objects? Yeah, pause the video and think about it. Okay, and now that you have all thought about this, hopefully maybe I can explain what's going on. So the point is that n choose k counts lattice paths from 0, 0. So, okay, what are these? What is each n choose k counting? For k, as k goes from 0 to n choose k is n choose k counts the paths from 0, 0 to the point n minus k comma k. And here k is a variable parameter. So you look at where can all these points be in the plane. And the answer is, so here's the first point is, this is k equals to 0, n comma 0. And the next one is here, n minus 1 comma 1, and etc. These are all points, 0 comma n minus k. Oh, sorry, that's supposed to be not n, but n minus k. Wait, hold on. Sorry, no, that's correct. Because k varies, and that's why. N comma 0, and then n minus 1 comma 0, and etc. Right? So, and well, so for example, this k equals to 2 corresponds to all lattice paths which come from 0, 0 to which basically get to this point. Now it's pretty easy to see what's going to happen, right? Because okay, every path on the left has to go from 0, 0 to n comma n. So it has to it necessarily is going to have to pass through a unique point on this kind of anti-diagonal. Every path. So yeah, maybe I should denote, let's say A is the set of all paths from 0, 0 to n comma n. Then each path in A passes through a unique point in this set 0 n comma 0, n minus 1 comma 1, etc. 0 comma n. So in other words, this set A is going to get split into these subsets. A is basically a disjoint union of A0, A1, etc., all the way up to AN, where A sub k is by definition it's the paths in A through which go through the point n minus k comma k. Yeah, so the size of A is 2n choose n, and the size of AK is, well, and that's where you would use the product principle. So if you fix one point, n minus k, yeah, maybe I fix this point, n minus k comma k, then how to account the paths which pass through this point? Well, each path is going to have two parts which are sort of independent. One that goes before the point, another one that comes after the point. And they can be combined. Just any path on the left can be combined with any path on the right. And that's where you get, and that's why you multiply. And of course, like the number of paths. Okay, so how many? What is the size of A sub k? It counts paths from 0, 0 to k to n minus k comma k, and then times the number of paths from n minus k comma k to n comma n. So if you want to count paths from from here to here, then you can make a change of coordinates, and basically the horizontal this rectangle here, it has vertical size n minus k and horizontal size k. So it's a k by n minus k rectangle. So and this rectangle has size vertical size k and horizontal size n minus k. And because of the symmetry of these binomial coefficients that we proved, they have the same size. So AK is basically n choose k. The size of AK is n choose k squared. I guess that's the end of the proof. Yeah, okay. So that's yeah. I think I can do one more problem. So the idea is basically you just look at the formulas. The formulas are suggestive. They tell you how you can, by just looking at the formula, you see the product, then there should be some pairs, and then you have the summation, so there should be some disjoint union in the background. Yeah, so that's there's some guesswork required, but basically it's usually pretty easy. Yeah, let me give you one more example of how you can do this. So here is another proposition, which is that some other weird binomial coefficients identity. The sum over k from 1 up to n, k times n choose k squared is equal to n times 2n minus 1 choose n minus 1. Yeah, I'm not even going to attempt to try an example. Yeah, maybe I'll try an example. So yeah, let's say example, maybe I should set n equals to 3 and see what happens. So I have the sum over k from 1 up to 3. So 1 times 3 choose 1 squared plus 2 times 3 choose 2 squared plus 3 times 3 choose 3 squared, which, okay, 3 choose 1 is 3, so that's 9. And that is also 9, and that is 1. So the answer should be 1 plus, well, the answer is 9 plus 18 plus 3, which is 30. That's the left-hand side and the right hand side is I have to multiply n by 2n minus 1. Yeah, okay. 3 times 2n minus 1, that's 5, choose 2. And 5 choose 2 is 10, I think. 3 times 10, I mean, it better be 10, is 30. So yeah, 30 equals to 30. Completely mysterious why that would be true. But through the power of combinatorics, we can prove it by just guessing what's happening in the background. So, and yeah, let's maybe start by analyzing the right-hand side. So there's n times 2n minus 1, choose n minus 1. So maybe so what's happening is that how do I, or maybe I should, yeah, maybe, yeah, let's even better. Let's try the left-hand side first, because it's almost, the left-hand side is almost the same as in the previous problem. In the previous problem you had n choose k squared without the k, but now you have the extra k. So what does this mean? That means that so the left-hand side counts lattice paths from 0, 0 to n comma n, which pass through n minus k comma k. Right. So far without any extra conditions, the number of such paths, so the number of such paths is going to be equal to n choose k squared, as we just computed in the previous problem. That's the, you have n choose k options in this rectangle and then n choose k options in this rectangle. But now I have to multiply it by k. So a nice way to formulate it is that so there's this line. Anyways, let me try to formulate it in the following way. So which pass through n minus k comma k with, so let me just say that there's going to be 0, 0, and there's going to be the point n minus k comma k. So, and there's going to be exactly k steps, exactly k vertical steps. So in order to multiply my number by k, I'm just going to say that out of the first k steps, one of them is special, with one special vertical step between 0, 0 and n minus k comma k. So I choose the first part of the path, the second part of the path, and then in the first part I just choose one step, maybe this step. I just decide that it's the special vertical step. And then this is an easy way to get an extra k multiplier for each term. Now, okay, now what I'm going to try to do is I'm going to try to explain why would the right hand side count the same objects but in a different way. The right hand side is n times 2n minus 1, choose n minus 1. Yeah, maybe now is also a good time to pause and just think about what do these numbers mean and why. So there's also a multiplier, right? There's an n, so you should pick a number which somehow represents the special step, and then the rest counts some lattice paths. So what would that be? And the answer is that, well, okay, here's a question. How many steps are between 0, 0 and n minus k comma k? The answer is that there's exactly n steps. 1, 2, 3, 4. Yeah, you can just label the steps and by integers between 1 and the sum of these two coordinates, which is n. So what you do is you first, let me continue here. You first choose the index of the special step. The index is just a number between 1 and n. So maybe what I'm and then what you do is you choose the remaining path from 0, 0 to n comma n minus 1. Right, so at this point I'm forgetting about the k and I'm only, so let me give you an example of what I'm gonna do. So let's say I choose, so again there's two steps. First I have to choose the index and then I have to choose the remaining path. How do I choose the, well, let's say maybe, okay, so n is equal to 3, or maybe let's do even n equals to 4. So I have to choose an index between 1 and 4. Maybe I choose 3. So 3 is my index of the special. The index is just the number of steps at which this special step appears. And then I also have to choose the remaining path from 0, 0 to n comma n minus 1. So here's my 0, 0, and n comma n minus 1 has coordinates 4, 3. So that's n comma n minus 1. And then I just choose any lattice path. Maybe something like this. That's my remaining path. And then the final step is to just insert the special step at the chosen index. So in other words, I have my index, which is 3. So I want my special step to be vertical and to appear at index 3. So I have 1, 2, the first two steps, and then I should have the special step. So the picture is going to look like this. I do 1, 2, these are the two steps which are the same as here, and then my special index tells me that I should have a special vertical step. And then I just continue as before. And because I have inserted a vertical step, I arrived at n comma n. But this is a special vertical step at index 3. Right. Again, index just means that if I just label all steps 1, 2, 3, 4, 5, 6, 7, 8, then I can just call my shot. Even before I can just insert it to be exactly at index 3, and then so this way, because I have chosen an index in n ways and have chosen the path in whatever binomial coefficient ways, I get exactly this many options for the right hand side. And now, of course, they are in bijection, right? In other words, so again, to recap, the right hand side counts just all paths from 0, 0 to n comma n, which have one special vertical step. and that special vertical step has to appear among the first n steps. And the first n steps are going to be exactly, so if you draw this anti-diagonal points, n comma n minus k comma k, then the requirement that the special index appears among the first n steps is literally translates it into the fact that it appears before hitting this main anti-diagonal. Now if you look at what at our interpretations of the left hand side, again, paths from 0, 0 to n comma n, which pass through some point on the anti-diagonal and have one special step before passing through this point. So that's the same set of objects, and therefore the numbers are the same. Anyways, I don't think the homework problems are going to be as tricky as this one, but I wanted to choose a tricky problem to just kind of explain what in what way can you try to guess these interpretations. And there is a lot of room for experiments, so you could instead of choosing lattice paths, you could choose sets of people. You can go read the book where you're choosing some committees and presidents of those committees and stuff like that. So sometimes it's easier to think in terms of subsets, sometimes it's easier to do lattice paths. Anyways, I think I'm out of time, so again, have a good weekend if you're watching this before the weekend. Otherwise, I hope you had a good weekend, and I will see you all on Wednesday. And don't forget about the homework, which is due on Friday. Thank you very much.